from Institute of Physics, Bhubaneswar. He will talk about Indian contribution in searches for beyond standard model Higgs bosons. About Professor Naik, he obtained his PhD from Day4 working the CMS experiment. So he has been working from beginning, and he is in fact one of the first batch of students that graduated from the India CMS collaboration. And then he held postdoctoral positions in Lisbon, Portugal, then Saclay, France, and then DG Hamburg. And currently he's faculty member in IOP Bhubaneswar since 2015. And his work, mostly his work contributions are charged Higgs and standard model Higgs. And he has also contributed some in that tau identification in the CMS quite a lot. So with this, I will request Professor Naik to take over, and let's keep the talk around 50 to 55 minutes and allow 5 minutes questions. Professor Naik.
Well, good morning. Can you see my slides?
Yes, yes.
Full screen?
Yeah, we can.
Okay. Okay. Thank you for giving me a chance to give this talk here. So I'll be speaking about the Indian contributions in the search for Higgs boson in beyond standard model scenarios. So there's one slide of motivation here. You have heard a lot about this already. So this plot you see in most of the talks, probably many times in this conference. And I put it in the first slide just to emphasize that whatever we have seen till now about the Higgs that we have observed 10 years before in LHC. So this Higgs boson looks like is a standard model Higgs boson. As you can see that the couplings to all the quarks and the gas bosons are and electrons are as expected from the standard model. However, we can as you saw in the previous talk, that this Higgs boson can be actually a part of the larger family, and we are only seeing one of them, which is a standard model like, and the rest of them are actually hiding from us. So the Higgs boson, such a very important aspect of the Higgs physics program at LHC, and it is the complementary to the standard model investigations or interpretations of its properties of the observed 125 GeV scalar particle. So when we say BSM Higgs searches, it basically inputs the searches for more complex Higgs sector, where there are predictions of additional Higgs bosons from many models actually beyond the standard model, and also there are searches for exotic decays of the observed Higgs particle, which are not possible within the standard model. So in this talk, I will only highlight the analysis where Indian people have made contributions. Okay, so just one slide about the searches. So as you saw previously, so particularly I'm just talking maybe the basic extension of the standard model. So the 2 Higgs doublet model or the MSSM, where you have 2 Higgs doublets. So you expect 5 physical bosons, and mostly they are controlled by the 2 parameters at the tree level in MSSM, MA and tan beta. So there are many searches actually. Many searches I have not even listed here, which are coming also in the higher extension models, like say CISO and other Higgs triplet models and so on. So these are the searches that I list here that are basically relevant to this MSSM Higgs doublet models. And the ones that I have highlighted in the red are where there are contributions from Indian students or Indian groups. So this includes, say, for example, Higgs, MSSM Higgs decaying to tau, or you can have also the Higgs decaying to 2, heavy Higgs decaying to 2 standard model like Higgs, and then going to P gamma or VP tau. There are several charge Higgs boson searches where Indian people have contributed. Then there are low mass Higgs searches, like say low mass 6 to gamma or high mass 6 to double and Dietary searches, which I'll be covering in this talk. Okay. So first of all, this is MSSM Higgs to tau. So I have marked which are the groups that have contributed here, and also the PAS and the CADI line, the CMS paper numbers here. So if anyone would like to add some new analysis which I may have forgotten, please let me know. I can add it later. Or in some places I have also marked the thesis number of some of the students. So I may have missed some of them. So please let me know. I can update the slides. Okay, so this is about MSSM Higgs to tau tau. So this is actually the flagship analysis for searching MSSM neutral Higgs boson at LHC, because so as you know, the MSSM Higgs, its production cross section, it's a proportional to the tan beta, which is the ratio of the active vacuum expectation in the two Higgs doublets. So it has enhanced coupling to tau if tan beta is large. So, and also if you there is also enhanced coupling to B. However, in case of Higgs to BB, you have large backgrounds going from the QCD. So in case of tau tau, you can have the backgrounds a little less compared to BB, as well as you can separate signal better with respect to the standard model backgrounds compared to that of the BB channel. That's why this is the most important channel for searching the MSSM Higgs boson at LHC. So here in this case, as you can see, the Higgs will be produced in two different modes mostly. So the gluon-gluon fusion, as like in the standard model case, but there is also additional enhanced production mode, which is Higgs production in association with the quarks, because of the, in particular at the high tan beta region. So the analysis strategy is typically divided, you divide the events based on the production and decay modes. So the decay channels are particularly based on the how the tau is decaying. So it decays to leptons or it decays to hartons. So there are 4 different final states that are considered. And then to separate the two production modes, you separate the production category based on the number of beta gates in the event. And in one of this, in the final analysis in round 1, so this is actually I'm describing about the analysis in round 1 where Day4 had my contribution. So it was the tau, PT of the tau was exploited to see the kinematic difference between the standard model background, particularly from the G to tau tau compared to the Higgs to tau tau. So they divide the events into tau PT categories. Okay, so one of the object identification where India has made a lot of contribution is development of tau identification at CMS. So during that period, just after round 1, where the round 1 Higgs to tau tau standard model analysis was actually based on the cut-based tau identification method, but just after that, there was a development of the multivariate tau discriminator based on the boosted decision tree to separate the taus from the jets using lots of kinematic information like say decay vortex, high impact parameter, and so on, in addition to the isolation. And with that, so you can see in this plot that these points give you the results and the expected performance of the cut-based tau identification, which as you see is as a function of the efficiency versus the misidentification probability. And with the multivariate method, this for the same efficiency, we had a factor of 2 reduction in the Z to tau packets. So that improved a lot this Higgs to tau analysis. Actually, this is the first analysis which used this MSSM Higgs to tau analysis is the first one that used this multivariate tau identification technique, and then saw that there is a large improvement in the result. Okay. And one aspect of this analysis, also same in the standard model case, is reconstructing the di-tau mass. So di-tau mass, as you see, because in the tau decay there are a lot of neutrinos produced. In case of hartonic, you have 1 neutron. In case of lepton, you have 2 neutrinos. So there are missing energies in the tau. So you do not get the full tau reconstructed mass just by combining the reconstruct the full di-tau mass by using a light fluid technique, which in CMS we call it a SP-FIT method. So it improves the resolution to about 20%. And then you can see here the left one is the visible di-tau mass, where you can see the G peak and the Higgs peak for the 120 GB is almost overlapping. While if you use this technique, you are able to separate them better. And for of course for the MSSM case, which is heavier, you get much more better separation. Okay, so the major backgrounds in these cases and multi-jet backgrounds. So G2 tau tau is typically measured in tau analysis using a tau mapping technique. So what you take is you take G2 mu events in data, then replace the mu1 by a simulated tau event. So this is partially simulated event, but the rest of the events come from the data. And then the double plus jets again is taken from the data, where you use a Peck factor method, basically a Peck probability of tau, a jet pecking a tau, use that probability to model this background. And then multi-jet events, it also is done in a similar manner, where two taus are fixed, and also you can obtain a separate method, the normalization, looking at the same sign taus. Okay, and the other backgrounds, which are basically small, are taken from the Monte Carlo. So here you see some of the plots from different categories, say no beta, and high PT, as I said, and low PT, and so on. So these are the top two are the mu tau categories, and then the bottom two are the tau tau ones. Okay, so these are the exclusion limits, as you can see. So the left side gives you the observed limits along with the expected one on the model independent branching ratio, a cross section times branching ratio for the gluon fusion case and for the BBH production case. Okay, and the right side one shows how much improvement we got with respect to the previous round to MSSM analysis, using this more information than here best tau identification and the PTB. So you can see that there is like 20 to 40% improvement with respect to this paper. Okay, and this was the interpretation. So there are actually many interpretations. I think just showing the two of them. The interpretation in a MSSM MH mark scenario. At that time, of course, there are different scenarios defined, and this is the one in this case, and the and light one is this MH mode pause scenarios. Okay, of course, the results have been updated with round 2, and you can find in my backup slide. So then the next one is search for low mass 6 to tau charge 6 to tau analysis. So this is actually the very first charge 6 analysis at let's see. There was also some contribution from here. So the search is that if the charge 6 is less than the mass of the top, then this will be produced in the top decay. So this is what you have exploited here. You have TT bar events, and one of the top can decay to charge 6. And depending on whether tau decays hadronic or to leptonic, you can have different final states. So we consider like E mu, and then E tau, mu tau, and tau plus jets kind of final states. Okay, and this was 70. Only half of the data of the 7 TB was used in this paper. And with that, so you can see, of course, here some plots. So here, this was the tau plus jet switch channel, where you use the transverse mass distribution, combining the visible tau and the missing transverse energy. Reconstruct this transverse mass, which was used to fit to obtain the signal. And in the other case, lepton and tau case, it was simply the counting experiment after the full selections, the number of events that you just count. Yeah, so with this, so with just 2.3 control inverse of data, there was a very strong limit on this, branching ratio for tau going to charge 6, and it was like 2 to 4%, depending on the mass from 80 GB to 160 GB. And this was interpretation in the MSSM scenario. You can see the large space of this parameter space was being excluded. In fact, by end of round 1, the full space was completely excluded. Okay. The next one is a search for low mass charges, which decays to a C quark and a S quark. So this kind of search is motivated by some of the 2Higgs doublet models, where you can see this is a type 2 2Higgs doublet model, but with a low tan beta region, where you can see for the low charge Higgs mass, you have enhanced branching fraction for the CS, also CB. Similarly, for a 3 2Higgs doublet model, even if it's a high tan beta region, so you also have a higher branching ratio for the C and S one. Okay, so this is another analysis by Day4 group. In fact, this was the almost fully Indian analysis, you can say. So this is here you have what we take is the final state with one lepton, which is coming from the W, and then 4 jets, okay, in the TT bar case. Then you can see what we do once we select this event. You just take the 2 jets which are assigned to say the Higgs, and then you reconstruct the dijet mass. You see this long tail in this case. So in this case, it will be very difficult to really separate the charges from the W. So if you get this kind of distribution, so what was done is use kinematic fit to reconstruct the full TT bar events in the lepton plus jet channel. So then once you do that, you get this kind of distributions here, okay, truncated and improved resolution. So you don't get this tail. And then you can also see it separates very well the W peak from the Higgs peak, where Higgs can be away from W. But at 80 GB, the Higgs is 80 GB, they will be almost like the same. But if the Higgs is slightly above 80 GB, then you will be able to separate the W peak. So in this case, this is since the starting point is TT bar, the major background is TT bar events. Okay, so with the round one, only with 8 TB, actually, the limit that was set was quite stringent. It was about from say 1% to something like say 6%, depending on the mass of the charges. And the same analysis was repeated again with 2016 around 2 data. So in this case, there was additional improvement in the round one time. We didn't have a possibility to tag a CZ. So this was possible in the round 2. So the CZ tagging algorithm was used to separate events or categorize events into 3 tag categories. We didn't throw events, but just categorize them. And so it improved the signal over background in tighter categories. As you can see, as you go to tighter categories, for example, you can see the enhanced signal in this category compared to the inclusive one. Okay, so with this, the result was improved with 2016 data, and now it is say like a fractional percent, and the maximum is less than 2%, particularly at the 80 GB, which is very difficult to separate. So the analysis with full round 2 data, 3 years combined, is still in ongoing, but there is improved kinematic fit and MBA based analysis is going on, so be completed soon. Okay, there is also some contribution in the charge is going to top and bottom, particularly in the high mass charges, where the Higgs is above the top work. So where it is produced along with the top and bottom or with single top. So in this case, the events are again selected with 1 lepton or with plus jets or 2 lepton, and then the events are categorized based on number of jets and p jets. So the major background is again TT bar, but they are separated into say TT bar plus light flavor or heavy flavor jets. So you see here just number of jets and p jets categories in single lepton and dilepton final states. So in this analysis, they use an MBA classifier, BDT in a lepton plus jets case and a DNN in a dilepton case to discriminate signal from the background, because this is a very challenging final state. And for the BDT, of course, they use different training, and for the DNN, it's a parameterized as a function of the mass of the Higgs. So here you see lepton channels in high jet multiplicity and B-jet multiplicity categories, and you can see that there are expected signal excess. Okay, and similarly for the DNN case in a dilepton category. Okay, so this is the results with the 2016 data. So you have model independent limit on the cross section times branching fraction for this one, and this is interpretation MHSM scenario. And here you can see in this plot, the contributions from 2 different channels, single lepton and dilepton. So single lepton seems to be more sensitive compared to the dilepton in this case because of the more number of events, particularly. Okay, Then I come to the Higgs resonant di-Higgs productions, okay, where say there is a resonant particle which can decay to 2 Higgs bosons, or a heavy Higgs can decay to 2 Higgs bosons. Okay, so these more searches are mostly motivated by, say, BSM models, where you can have extra dimensions producing, say, spin 0 radiations or spin 2 gravitons, or also like, you know, NSSM models, you can have heavy Higgs which can decay to lighter Higgs bosons. So these are the kind of production modes. In this case, you consider 2 B-quarks coming from one of the Higgs and 2 photons coming from other. So this channel is very useful in the case that this enhances, because of the B bar, you take B bar, it enhances the branching fraction, while you take the photons in other leg, that helps in tagging the events or identifying the events, as well as triggering at the, you know, at the trigger level. Otherwise, it's not easy to trigger with only B bars. So the photon selections in this case is very similar to the standard model Higgs to gamma gamma analysis. And then you select the 2 beta jets. Then you make a full mass of this resonance by combining all these momentums. Okay, and then there is resolutions. So this is shown here, that if you just take just a combination of 4 particles, or if you do these corrections, how it improves the resolution at different mass points. Okay. So in this case, the major backgrounds are gamma gamma plus jets, and standard model Higgs to gamma gamma as well is one of the background in this case. So they use multivariate classifiers to categorize the events. The input to these classifiers are basically kinematic variables, beta gain scores, and the helicity angles of these events. And then you divide the events based on the BT output and also the region of mass, divided according to the mass regions. So here you can see, for example, the distribution of the mass. This is the occurring background that's shown in the data. And then we have the resonant double Higgs production, and also non-resonant single Higgs production shown in this plot. And this is one of the helicity angles that is shown here in Pauline super plane. Okay. So the signal is extracted using a parametric fit in the gamma gamma jet mass plane, and the signal is modeled using the double-sided crystal ball function, and the backgrounds are modeled using polynomials, and the standard model Higgs background is also modeled using a double-sided crystal ball function. So this is the limit that you get. So this is based on as a function of resonance mass, but the limit is on the cross section times branching fractions on this particular final state. And I think so. This is the left side is for the limits for the spin 0 resonance, and for the right side it is for the spin 2 resonance. Okay. A similar analysis is also performed in the BB tau tau final state. In this case, you don't have that much resolution like gamma gamma, but the branching fraction is much more enhanced because of the tau as well. So this is the same motivation for searching for this particle. So in this case, you basically take again the 2 tau leptons and 2 jets, and you reconstruct. This is a similar analysis like MSSM analysis, where you reconstruct the di-tau mass using the likelihood method, and then apply some parts on them. Then similarly, you reconstruct the di-jet mass using a kinematic fit, and then the full discriminant is used at the mass of the 2 combined mass, inherent mass of the 2 explosion. Okay, so in this case, the events are categorized to enhance the signal over background using number of B-jets in the event. So you have 0 betax, 1 betax, and 2 betax to enhance the signal in this case. Okay, the major backgrounds are G2 tau tau in this case, which are estimated similar to the earlier I have discussed this, and the multi-jet backgrounds, which are estimated using the tau vector method, and the TT-bar backgrounds, which can be modeled from the Monte Carlo. So here you see some of the di-Higgs mass distributions in different categories. So 2 beta categories, 0 beta categories, and 1 beta categories. And you see the possible enhance of the signal in different categories. Okay, so the upper limits is obtained in two different scenarios, assuming spin zero resonance or spin to resonance. So here you see, upper limits observed, both observed and expected, and here you see, for example, the possible theoretical cross section that we expect from two different radian, two different parameters. Similar cases here as well with for the spin to case. Okay, so this result has also been updated in 13 dB, which provides more stringent limits. Okay, then I come to a low mass standard model like Higgs to gamma gamma search. So this search is motivated by the presence of additional Higgs in several BSM models like 2Higgs doublet model, NMSSM, and so on. So the search region is here. It's from 70 to 110 dB, mostly restricted by the trigger that you can event. That you can trigger an event. So the standard model light is because here the relative contribution of the production processes are assumed to be similar to that of the standard model exposure. That's why it's called standard model light search. So the analysis strategy is very similar to the standard model Higgs to gamma gamma analysis. So, but there are two major challenges in this case. One is that first of all, you have to trigger the event with 70 dB. Typical for the standard model analysis, the trigger threshold is much higher. Okay, on the 4 diphoton trigger, but here it is difficult to do that. So you have to lower the mass range. So you can have to lower the PT. So that was the challenge. And then another one is that it falls in the region of also G to E, where electrons can be misidentified, and basically they are not reconstructed as electrons, but can be reconstructed as photons. So this is like double fake background coming from G. So these two are the major challenges in this case. So there is dedicated HLT path flash constructed for this analysis with the tighter photon identification criteria, but the PT and the mass on the diphoton was relaxed to get this, to trigger these events. And as you have seen probably yesterday also, and maybe today, I don't know. So this identification of the photons are done using the BDT-based multivariate method, and here there are a lot of contribution that comes from the SNP in identifying the photons, and for a long time they are working on this. Okay, and again, as I said, the BDT was used not only for photon identification, also for event categorization. So there is, you can see the event-based BDT here, diphoton BDT, and then the events are based on the BDT score, which were divided into various classes. So you have three classes of events based on the signal over background ratio, and then the three classes are put together to extract the signal. So again, the signal is modeled using Gaussian distributions, but to get the parameters of this Gaussian, we use the Monte Carlo samples from 7 to 210 dB, and then fit the Gaussian distributions, some of the Gaussian distributions to get this set. And okay, then for the backgrounds, for the continuum background, it is analytic functions for this, and for the double fake background coming from the G events, so they again use this double-threaded crystal ball to model these ones. Okay. So here you see the the obtained limits on the cross-section times branching fashion for this production channels as a function of the mass of the Higgs. So as you can see here, the sensitivity is already low, quite low at the 90 dB, where the major background is coming from these double fake events. And there is a slightly little excess here, in this case, around 95 dB. And maybe you can see this p-value plot here, which shows that this excess is about, say, like 2.5 or 2.7 sigma. Okay. Okay, so there are analysis for the high mass searches. So high mass Higgs to WW. So here, similar assumption is made, like the couplings are standard model like. So it is motivated by models like standard model with one real singlet field, which gives heavy Higgs bosons, which can decay to two light Higgs bosons, which can decay to WW or ZZ. So this results in say additional resonance, which can decay like a standard model Higgs bosons. So in this case, there is one important factor that needs to be taken into account is this interference. So this signal interferes with, say, the off-cell standard model Higgs production, and also the standard model WW background. So you can see in this plot that the black line is without the interference for this signal. For example, if you consider, say, 700 GeV resonance heavy Higgs, then the interference which, say, so the interference with the standard model Higgs off-cell contribution is given in the red, and then the interference with the background, WW background, is in this blue. So at the end, what you get is this green color. Okay, so the signal contribution is extremely reduced due to this interference effects. So here the search strategy is basically divided based on the number of channels in the categories. So here they have considered two channels, dilepton and lepton plus jets. So the dilepton, we have either same flavor or a different flavor, like mu, for example, or EE and mu. So this consider different production modes, say VVF production mode, or VVF along with a gluon-gluon fusion, but the gluon-gluon fusion is separated into, say, 0Z, 1Z, and 2Z to enhance the signal, basically to take the boosted ones or VVF-like events and so on. And similarly for lepton plus jets, they have also considered the reserved categories as well as boosted categories, where W can be boosted, where W decays to jets. One of the W decays to 2 jets. And so they also use the vector boson fusion or gluon fusion production category. And gluon fusion is actually tagged using a so-called this Mela discriminant, this matrix element light load method, which is used to construct the discriminant for this to identify a gluon fusion process. And then you add additional kinematic codes of beta vectors to reject the backgrounds. Okay, so the final discriminant is this dilepton channel is this so-called M-repo reconstructed mass, which is combination of the missing PT and the dilepton momentum. So here you see the distributions for this final discriminant for various production categories and channels. So here it's a same flavor mu VVF category, and here, for example, different flavor like mu, and then the VVF and 2Z categories. And here you see the expected signal contributions for different mass of this resonance. Okay, for the lepton plus jet channel, since you can reconstruct both W's, so they reconstruct the full WW mass in this case, and you see the WW mass distribution for the gluon-gluon fusion category and VVF category. Okay, so this is the limits that have been obtained in this analysis. So in this analysis, they have actually assumed different fraction of the VVF contribution in the production category. Depending on the what fraction they have used, they obtain different limits. So for example, the left one, it assumes the same fraction as the standard model in case of VVF production. So you get these limits here, and you have stronger limits on the production on the mass of the WW resonance. So you get almost like, say, 1.8 eV or so. And while you assume the floating for the fraction, you float this fraction of the VVF contribution. So then the limit on this mass is significantly reduced. They have also assumed, I think, a VVF equal to 10 or something. You can have a look at it. Okay. And then they are also interpreted in various MSSM scenarios. So here, for example, interpretation in HMSSM scenario. So this is expected one in the shaded and the observed in the dotted lines. Similar interpretation in 2X doublet model in the type 1 2X doublet models, where you can see the limits are a little bit less stringent compared to the MSSM case. Okay, okay. So there is an update on this analysis with full round 2 data in dilepton channels. So in that case, they have improved the analysis by using the deep neural network based event categorization. So the deep neural network is used to categorize events into gluon-gluon fusion or VVF or background. And then instead of using this mass of the M-repo or mass of the double boson, they again use TNN based mass regression, you can say, DN-based double mass reconstruction in this case. And then the limits are in fact stronger compared to the previous one. Of course, they use more data in this case. And then here is one of the interpretations in MH125 scenarios. Okay, a similar search is also performed in Higgs to ZZ, so, and then there is also contribution from Indian side here. So they consider 3 final states for lepton, depending on how the Z is decaying. So 4 lepton, 2 lepton, 2 quark, or 2 lepton with 2 neutrino, where one of the Z decays to neutrino. So in this case, they also consider both gluon confusion and electric production. I say electric, they include also the WH and VH channels in this case, but that contribution is probably negligible. And they categorize events using a matrix element technique to VVF or non-VVF categories. And they use this so-called Miller discriminant in 4 lepton and 2 lepton 2Q channels, where the Miller discriminants are constructed from the angles that you can see in this plane. So there are 5 angles I think defined in this plane for gluon confusion and VVF production processes. And then in case of 2 lepton 2 neutron channel, they use the transverse mass to extract the signal. So here you see this Miller discriminant for the 4 lepton channel. So you have this distribution for the background and what you expect from the signal for different values of the MX, and they also consider different widths of this resonance from 0 GB, 10 GB, 100 GB, and so on. Okay, and this is transverse mass for the VVF category in 2 lepton 2 neutron channel. So this is the exclusion limits on this analysis. So you can see this is exclusion limits are provided in on the branch say cross section branching fraction for different values of MX, as you see in the x-axis in this part, but also for several values of the width of this resonance. So here, for example, I show only width 10 GB, but they have also considered 1 GB and 100 GB and so on. And also for different values of the fraction of the VVF contribution, which is a P parameter. So in this case, in the left case, you can see that this is floated, the VVF contribution is floated, while in this right case, the VVF contribution is assumed to be standard model. Okay. Okay, so this is all I discussed about the standard Higgs sector. Now I come to a new or the Higgs decay case. So before going to the analysis, just one slide about the motivation. So you see this, we know that the width of the standard model Higgs is small. So the couplings to BSM a small coupling to BSM can actually result in detectable branching fractions. And as you see this, I actually saw Atlas plot because that is probably the latest one I took. So as you can see, this is the combined fit of all the Higgs properties from all the Higgs channels. So as you can see, if we allow floating values for the undetected one, so you get a constraint on the undetected branching fractions for the Higgs to be order of 10% in case still it is maybe close to 15 or maybe 17-18% at 1 sigma level. At 2 sigma level, and at 1 sigma level, you can say like say order of 10%. So you have order of 10% decay still allowed at this level to decay into unobserved particles, and you can see the same thing in this plot. So if you assume the invisible and the undetected contribution to be 0, so you get a compatibility between, say this is a coupling modifier to the effective gluon coupling and photon coupling to the Higgs, and this best fit value is compatible with the standard model expectation. If you calculate the p value for that, you get say 51%. But if you allow this to be floated, this invisible and undetected, then you get a better, p value for this compatibility. Okay. In this case, the right one case, I think they include also the invisible analysis results from the invisible analysis into this fit. So that basically says that you still have like order of 10% possibility that then the standard model Higgs boson can decay to, or the observed Higgs boson can detect to unobserved particles, which you still don't know. Okay, so because of this, there are many motivated searches one of such searches is searching for Higgs decaying to two light Higgs bosons. Okay, so this search is motivated by next to MSSM Higgs sector, which is basically have MSSM Higgs sector plus one more singlet field. So that adds more degrees of freedom. So you have 7 Higgs bosons. So 2 of the Higgs boson can be lighter than say the standard model one, and one of them is scalar or pseudo-scalar. So the generic search assumes that A can be scalar and pseudo-scalar, and there are many searches actually. You can see the list here at the LHC, and one such contribution is also made from the Indian side. So one of the A decays to 2 B quarks and another decays to 2 muons. And these searches are actually quite challenging because you have basically you have to trigger those events and then also identify the particles at low PT. So this is a promising search channel for searching Higgs to A bosons. So this is relatively large branching fraction because you consider A to BB, so the fraction is large, and then you consider mu, which helps in again triggering as well as identifying these events. So this analysis considers actually 2 similar analyses, not only just A, but also there is another analysis. I will come to it. Is to ZA decaying to same final states. So there are some probably difficulties in producing the signal samples, so they have generated signal samples privately. So in 2016 analysis, there was already something like 20% improvement, better results or better sensitivity in the same channel compared to the Atlas. And the Indian groups actually, this is the result from the 2016. And then the Indian groups actually, I think, contributed to the full drawn to analysis and using the 2017 and 18 data. So this exploits for the full drawn to exploits latest B-tagging identification criteria like say deep CHV and so on, and then the extended mass range and the re-optimized analysis chain. So here you can see actually one of this plot for the full mass of the Higgs boson constructed from this full final state particles, and you see that this mass distribution peaks around the standard model Higgs boson, while the background is looking like this. Okay. Okay. So yeah. As I said, this search range is between for the mass of the A range that considers 20 GB to 62.5 GB. So it selects events with 2 muons and 2 BJets, so 1 tight and 1 loose. And depending on second BJet, they categorize the events into tight, medium, or tight loose. How it is tagged is a second BJet. And the mass covered from the mu decay product, it's kept 1 GB off compared to the mass range search range. Okay, so 1 GB less and 1 GB higher this range. And then a chi-square variable is defined to select the events, which basically checks the compatibility of the mass between the 2 B quarks and the 2 muons. So they should be similar within their resolutions. And also the mass of the full di-Higgs or di-A production is compatible with the mass of the Higgs. So that is the chi-square variable that is defined. In this case, the major backgrounds are Delian plus BZ production and TT bar events, and the search is performed using binned light load bit to mu distribution in data, and simultaneously in all three categories. So here you can see this chi-square distribution that I discussed. So the chi-square, as you can see, the chi-square for the signal looks like this. So basically maximum is around 0, while for the background it is more or less flat, maybe slowly falling. Okay, and this is below. You can see one of the di-muon distributions for the by fitting the data to the background model. Okay, so this was the limits on this production cross-section times branching ratio. So here the limits are normalized with respect to the cross-section from the standard model. So there's already quite stringent limit from the 2016 analysis, and there are a lot of fluctuations, but all of them lie within this 2 sigma band. around the expected value. And they have also added this result to the full interpretation of the Higgs to AA analysis, all of them combined together in 2016. So here is one of the interpretation into doublet model plus S type 2 scenarios with tan beta equal to 2. And this one contributes particularly in this high mass 20 to 60 GeV region here. And there are other tunnels which can extend up to, up to almost like QG. Okay, so here it's the further contribution, particularly the contribution in the using the 2017 data, where they improved with respect to 2016, particularly using the improved bitting algorithm. Initially, it was the combined secondary vertex algorithm. Now there is DNN-based combined secondary vertex algorithm. It's called deep CSV. So that further improved the analysis, the results or the limits on this production channel. And as you can see, 5 inverse of more data compared to 2016, you can see that this red is almost like factor 2 improved compared to the 2016 results. Okay, okay. As I said, there is another analysis very similar. The Higgs going to ZA, going to BB mu. So in this case, the analysis is almost similar to what I said before, except that the BB1 mass here is compatible with the G boson mass instead of actually not that stringent, as you can see here. This is on the production time, cross-section times branching fraction. This is normalized to the standard model one. So this is less stringent compared to the previous analysis. So it requires probably more, better analysis techniques to improve the sensitivity in this case. Okay, so that's it that I discussed. So there are a few more analyses still ongoing with full run-2 data, particularly these ones that I list here, which has also measured Indian participation, these two HH, BB gamma gamma, which I already informed before. Then BBWW, then A to ZH, where H becomes to tau tau, and also Higgs to charge Higgs with full run-2 data with improved kinematic fit and multivariate. Okay, so that brings to my summary. So the REACH program to search for new physics in the Higgs sector at CMS. There are significant contributions from Indian side, especially from our students in many important searches, having a leading role in some of the analysis. There are quite a few analyses still ongoing with full run-2 data, and we are looking forward to exciting results in round 3 and beyond. Thank you.
Thank you, Professor Naik, for the nice comprehensive overview of BSM Higgs search by Indian groups. So let's open the platform for questions from participants. I would like participants to raise the hands so that we can go one by one. Okay. I don't see any questions, and we are already close to 12:30. So
I think
Kajari has one question. Kajari, I would like to now, you are raising hands, and also I would like to hand it over to you at the end of the sessions. Please go ahead.
Okay. Basically, Arun, what Professor Rajiv Gawai was asking earlier, maybe you can give the example of the involvement in charge Higgs analysis.
Yeah, which example? Sorry.
Means in principles where all Indian contribution has been. Specific examples regarding charge Higgs analysis. So you can just mention a bit details.
So okay, let me go
back. That already. Anyway, nice talk first of all. But
thank you. Yeah, so this analysis charge Higgs to tau nu, it was actually not that much Indian contribution. As I said, there is actually some theoretical inputs, mostly from Manoranjan, Professor Manoranjan Guchai. But this analysis was mostly led by.
What with Professor DP Roy? Let's talk.
Yeah, but DPRI was not part of CMS, but okay. But in the CMS analysis itself, so there was some inputs given from Professor Manoranjan Gupta. But this analysis was led by actually Lisbon and Helsinki groups, where I was mainly from the Lisbon side. Okay, that's why I included it here. But the second one, charge Higgs to CS, is fully Indian. You can say I listed two thesis here. One is thesis from Gorango Kole, Day4, with Ron data, and then second one is Ravindra, who did his thesis here with the 2016 data, and the third one we are currently working with pulled on to also from the Day4 and side on this. So there, of course, I was always part of this, but yeah, two Day4 students were the leaders in this analysis. Yeah, so there's another one, TB. I'm not exactly sure how much contribution, but yeah, there are people from Punjab, which I found they have contributed to this analysis.
Okay, thank you, Kajari. Okay, sorry, go ahead. Yeah.
Okay. Ram wanted to talk.
Hello, Ram?
Yes, Ram.
Yeah, so regarding, I think the thesis 2090-398, that's actually my thesis, not Ravindra's.
Which one? Sorry.
This one. Yeah, certain thesis 2019-398, the 398 one.
But 398 is attached to BB.
You said Ravindra.
No. What is it? BB Tau, I think I attached to 398 yours.
Yeah, BB Tau and MSSM. Yeah, this one. BB Tau and MSSM mixed.
This is your. But I think I said Ravindra in CS. Yes, Higgs to CS. Charge Higgs to CS. This one. 293.
Yes.
Yeah.
Okay, Kajal, up to you now to take it up. Yeah.
Nice. So let's thank all the speakers of the day, and thank you, Professor Sanjay Singh, for taking your time off. You are so busy, so thank you. So we meet again at 2:30. So let's give a big thank to everybody. Shashi, you want to say something?
No. Oh, sorry, I was unmuted. Okay.
Yeah.
No.
Okay. Thank you.
Thank you. Thank you.
Bye. Bye.
Bye.